let's take a look at an example where we will go through and prove that the limit of a particular function, g of x, at a point, so the limit of g of x at 4, we're going to prove that the limit of g of x at 4 is equal to 13 halves when our function g of x is defined in this way here, right? So we need to show that for every single choice of epsilon, there exists a choice of delta, which is often built on the choice of epsilon. So for every choice of epsilon, there exists a delta, so that whenever our value of x is within delta units of our value of c, so within delta of units of 4, that our function value evaluated at x is within epsilon units of the limit, which we claim to be 13 halves. So we're going to go through, we're going to do some scratch work first, and then we will write this proof more formally. So our scratch work is this. We want to have, or we want it to be so that if we are given an epsilon greater than 0, we are going to find a choice of delta greater than 0. So that when that value of x is within delta units of 4, right? And so that 4 is coming from our value of c, the limit we are heading, the value where our x value is heading towards. So whenever we're within delta units of c, we want that to imply that the distance between our function, g of x, so 2x plus 5 over x minus 2, and the limit, which we claim the limit was 13 halves, so we want the distance between our function and our limit to be less than epsilon. Right? So we don't have that yet. We're going to try to come up with a choice of delta that will ensure that to be a case, right? No matter the choice of epsilon. Right? And so we are going to play around with this stuff here. So 2x plus 5 over x minus 2 minus 13 halves. If that is, so when we take a look at that, get some common denominators and whatnot, we end up with 4x plus 10 minus 13x plus 26 all over 2 times x minus 2. And so that would be negative 9x plus 36 over 2 times x minus 2, which gives us 9 halves x minus 4 over x minus 2. All right, so we could factor out a negative 9 from the top, but we're taking the absolute value. So we have the absolute value of 9 halves times the absolute value of x minus 4 over x minus 2. Absolute value of 9 halves is positive 9 halves. Right, and so we get this. But remember, what we wanted to have happen was we wanted to put a restriction on the absolute value of x minus 4. But we have this x minus 2 on the denominator, and so that seems maybe a little bit problematic, right? So I'll take this a step further. So we would have the absolute value of x minus 4 needs to be, so if this is going to be less than epsilon, then we need to have x minus 4 to be less than 2/9 the value of epsilon times the absolute value of x minus 2. right? And so that's where the problem is. That's our issue. And so here's what we're going to do. We're going to just make this arbitrary restriction. On delta. Right. So we're going to make some arbitrary restriction on delta. Let's say delta is going to be less than 1. Right. You might say, why did you pick delta less than 1? What if I wanted to pick delta less than 2? And I would say, okay, pick delta less than 2. That's fine. We are making an arbitrary restriction. Right? So if we make that restriction, then this would tell us that the absolute value of x minus 4, if that is going to be less than delta, then we have the absolute value of x minus 4 is less than 1 because we're choosing our value of delta to be less than 1. Or we could say that negative 1 is less than x minus 4 is less than 1. And so we would have x minus 2 is between 1 and 3. Right? So if we've made this arbitrary restriction on delta, then if our value of delta is less than 1, we're going to have x minus 4 over the absolute value of x minus 2. If that is less than 2/9 epsilon, and the value of x minus 2 is between 1 and 3, so that the absolute value of x minus 4 is less than 2/9 epsilon. So what we can do is we can choose delta to be equal to the minimum of either one, that arbitrary choice that we made, or 2/9 epsilon. So we're going to choose delta to be the smaller of these two. Right? So this is all just scratch work. We haven't actually formally proved this yet. So now we're going to go through, and based on all of that scratch work, we are going to prove this. So given epsilon greater than 0, let delta equal the smaller of the two values, the minimum of 1 and 2/9 epsilon. If this is true, then our choice of delta is less than both 1 and that choice of delta is also less than 2/9 epsilon, right? So it is the smaller of those two. And I said let delta equal that minimum. That's not really what I want to choose. I want to choose a value of delta that is actually smaller than that minimum. Then our value of delta is less than both of those. And so if we have the absolute value of x minus 4 is between 0 and delta, then we have the absolute value of x minus 4 is less than 1. Because it's less than delta, and we observed above that delta had to be less than 1. And so 1 is less than x minus 2 is less than 3. And also, we have the absolute value of x minus 4 is less than 2/9 epsilon, which would imply that the value of x minus 4 over the absolute value of x minus 2 is less than 2/9 epsilon. Right? So we can say that because our choice, so this value of x minus 2, that value of x minus 2 has to be between 1 and 3 based on our restriction here. So that value of x minus 2 is between 1 and 3. So if we divide by something that is bigger than 1, it's going to make this, this overall fraction on the left smaller. And so if we divide by something more than 1, this is getting smaller. If it was already smaller than 2/9, it's going to be even smaller than 2/9 epsilon. It will be even smaller than 2/9, further away from 2/9 epsilon. All right, so we have that has to be less than 2/9 epsilon, which would then imply that if we were to multiply both sides by 9/2, that will be less than epsilon. But this left-hand side is actually the original function, the absolute value of the original function, minus 13/2. So that left-hand side is this, which is less than epsilon. So in this proof, we have shown that no matter what choice of epsilon we might choose, given any epsilon, we could choose, there exists a delta that will say whenever our distance between x and 4 is less than delta, the distance between the function value and 13/2 has to be less than epsilon. And that is our proof. That was a tougher one, and not all proofs are quite as straightforward as maybe the first example that we did in our last video. All right, we'll talk to you guys later.